So welcome all the people from Interpol and abroad. I'm very happy and honored to give that interview of Professor Ghislain de Marsily, who was awarded Interpol Time Capsule. So we are several interviewers, Mickaele Ravalec, a colleague of mine, Michel Quintard, who is president-elect of Interpol, and myself from IFPN, who supported that video. So now we will go back to the questions.
As we shall see later on, you did a lot for hydrology in France, but also all over the world. Could you please tell us now a few words about you as a kid, but also as a student, and explain the reasons that led you to hydrology?
Good afternoon, ladies and gentlemen. I'd like to thank Interpol for organizing this type capsule for me, and also the French Institute of Petroleum and New Energy for organizing this recording. And then, of course, my three friends here, Mickaele Ravalec, Michel Quintard, and Benoît Noetinger for organizing the questions. So I'll start with my childhood. I was born 1 month after the start of World War II in October 1939. And of course, this war was very instrumental in the development of my personality. I grew up in a farm. And the reason I grew up in a farm is that my father had already lived through World War I. And he didn't want to have another war in Paris. And so he bought a farm in southern France where I lived, and I grew up until I was about 14. The major thing that happened to me during this war period was that when I was 8, I got polio. And I had to lay in bed for about a year. I couldn't move, I couldn't talk. See, I could talk, but I could not walk. And of course, this had some large influence on my studies and my development. What did I do during my farm years? Well, I helped to farm the land with my parents, and I was in charge of catching rabbits because we didn't have much to eat during the war, and there were a lot of rabbits in the forest behind our house, so I helped to catch rabbits and eat them after. Then, when I got polio, I could not go to school anymore. So I had to learn at home, and I was taught by my mother and my father and other persons who taught me how to read and write and do some math and so on. And I didn't go to school until I was, I would say, 14. Because at that time it was also very difficult to move around, and I could not go to the village by car. There was no petrol for the cars, so we had to walk or to take bicycles, and I couldn't do that, so I learned at home. What happened is that I finally got back to walk correctly, I think, and I was decided to study in an engineering school. We have two different routes in France to study. One is engineering schools, and other is university. So I started going to engineering school, and although my intention was to study chemistry, I didn't succeed in being accepted in the chemical school, and I ended up at École des Mines de Paris, the Paris School of Mines, which was a good school of engineering. So I started studying there, and the courses which I really liked a lot was geology. So at the School of Mines we had to select one option, which would be the major in which we would graduate. And I decided I would go for geology. So I went to see the professor of geology, who was a very famous geologist. His name is Jean Gogel. He was a tectonic geology. And I asked him, Monsieur le Professeur, would you agree to take me in your course so that I can become a geologist? Then he looked at me and he says, no way. I saw you walking into my office. You have problems walking. A geologist must walk and cross mountains and rivers and whatever, you will never be a geologist. Please leave my office. The answer is no, I don't want you in my class. That was a little bit tough, and I didn't appreciate that very much, as you can imagine. So I studied hydraulics, which in the end helped me a lot also. But when I finished my schools, I wanted to work, and I decided I would work in the public works company, a firm who was doing public works. And this firm hired me and sent me in the Sahara Desert to drill oil wells. That's how I started, and I became interested in fluid flow in porous media. Then, after 3 years of doing that work in a public work company, I became fed up with that. I didn't want to, build things. I wanted to study the plans to building things, but not the actual work of injecting cement, drilling wells, and so on. This was not what I wanted to do. So I went back to the university for 1 year, and I studied hydrology. So my interest in hydrology came from the refusal of Professor Ghislain to have me in his geology course, and my lack of understanding of hydrology, which interested me. So I went to the university, and I liked a lot learning about hydrology and groundwater hydrology in particular. And then when I was over and was finished that, I was offered a job at the Paris School of Mines for 1 year to do some research in hydrogeology. Well, I did. I said, okay, I'll work for you for 1 year. And in fact, it lasted 20 years. So I stayed for 20 years of my career doing research in hydrogeology. So my research in the Paris School of Mines on hydrogeology was essentially in mathematical hydrogeology. I learned to program, and I wrote computer codes, a little bit similar to ModFlow, to solve the flow equations on a computer. And after a short while, I was interested in the inverse problem, which I'm going to talk about in a moment. So at the same time I was doing research on mathematical hydrology, I was asked to teach a course at the Paris School of Mines, and I gave the title of this course Quantitative Hydrogeology. And when I had taught that course for several years, I decided I should write a book, which is here, which is called Quantitative Hydrogeology, which is in English, and which has been used by many generations of students in different countries to learn mathematical hydrogeology, if you want.
Ghislain, you were in close contact with Georges Materon, a name that young scientists discover when they are looking at the root of geostatistics. Could you tell us a little bit about this encounter, and to what extent it determined or oriented some of your future research?
So this I found very interesting and useful for estimating the permeability, but what I developed, and this may be an answer to one of the questions that Benoît asked, what is my major contribution? It's the development of what is called the pilot point method, which I developed with the help of the French Institute of Petroleum, and which is this is the equation. You have here the standard Quijing equation, which I have just shown you a moment ago. It's that the estimated value at the point x is a sum of the measurement points, and I added to that a new term, which is based here, which comes up here in this equation, which is the sum of the lambda j times what the transmissivity or the permeability at what I call the pilot point. And these are invented points. They do not exist. It's not a measurement point. It's a point which is added to the Quijing equation, but the value at these points are unknown. The Quijing equation does not take into account the value of the parameter you are estimating, but just the location where the measurement is made. So you can write a Kriging equation even if you don't know the value k of x at the unmeasured location. So you can take these values to be unknowns, and then you write an estimation equation where you want to have the estimated head, the measured heads. This would be the same aquifer. This would be the same aquifer, and the dots that you see here are the measurement points of the hydraulic head. And of course, the hydraulic head and the permeability are related through the flow equation. And once you solve the flow equation with the Krige transmissivity, you get the computed heads. And the computed heads, you want them to be as close as possible to the observed heads. And you can write an estimation equation where you optimize the value of the permeability at the pilot points in order to get a good agreement between the measured heads and the observed and the calculated heads. And this is basically the method of the pilot points. You select the location of the pilot point. You can have as many pilot points as you want. You fix those the values as unknowns, and you optimize the value of the unknowns with an optimal head difference between the observed and the calculated ones. So this method was published, and surprisingly, the person who caught on that method the best is an Australian. His name is John Doherty, and he developed a code which is called PEST, which is to apply the pilot point method to any problem of estimation for the inverse problem. So it has been very much publicized by the work of this Australian colleague, whom I met only recently. Initially we never talked. He came to me only 20 years later, and we discussed the pilot point methodology, but he developed this PEST code, which is rather widely used, based just on the papers I had written on that.
A great number of papers has been published in the past decades about the so-called abnormal or non-Fickian dispersion, with many proposals to take care of such complex phenomena. While your generation in its early activity could not take advantage of the computational and observation devices the young people have today, it is quite impressive to see so many ideas still on the table. So my question is twofold. First, how do you see the future of this research field? And do you believe the directions that should be followed are clear enough? And second, as a professor who taught hydrology for many years, would you say that the concepts are robust enough to be included in a 2020 textbook?
Okay, the theory of dispersion in the late 1970s was still based on the work by Scheidegger, who was a Canadian scientist, and according to him, the dispersion coefficient, which measures the mixing of particles while they are transported in porous media, the dispersion coefficient was to reach a plateau after a while. So we were all convinced that the dispersion coefficient became a constant, not initially. Initially it grew with the displacement, but eventually it reached a plateau. And then in the late 70s, there were a few experiments in the fields, with large-scale experiments done mostly in the US, where one realized that, in fact, the further away the plume of pollutant was spreading into the aquifer, the larger the apparent dispersion coefficient became. So the theory of Scheidegger was not perhaps firmly established. At that time, two US researchers, Gelhar and Naff and Gutiérrez, published a paper in '79 where they found that for a stratified medium, I'm going to talk about dispersion in a stratified medium. So you can see here a stratified medium. You have layers. Each of these layers have a different permeability. Therefore, the velocity of the pore fluid is larger or smaller as a function of the permeability. These are the arrows which I have drawn here, which show the dispersion or the difference in velocity. Because of these mechanisms, you have a tracer would disperse longitudinally in the sense of the direction of flow, but also transversely due to microscale dispersion. So this is the 1980 paper, which shows that, in fact, the dispersion coefficient can go to infinity if the covariance function of the velocity over the vertical doesn't take a very special form, which is the Hall effect covariance function, which I've shown. And if you don't have that covariance function, then you have infinite growth of the dispersion coefficient with distance, travel distance. So this was, I would say, a sort of a nail in the coffin of the theory of dispersion, because it showed that the dispersion coefficient could increase at infinity. And this, I believe, is the reason why this paper is still famous and used, referenced today. Now, about the question of does this theory need to be included in textbooks on hydrogeology, the answer is yes. I mean, no one today would consider speaking about dispersion without mentioning the growth of the dispersion coefficient with the distance, the travel distance, and therefore every book today has a section which describes the theory of dispersion based on these observations in field tests and this theory which Matron and I had developed.
Besides your research contribution to hydrology, your contribution as a student teacher and advisor, you also played an important role as a citizen, bringing scientific perspectives to contemporary important problems like the question of water resources, pollution, global climate change. Could you describe your main actions as a scientific expert providing advices about topics of public interest? What were your motivations? What do you think about the social role scientists have to play?
Well, what I remember with a lot of fun of my professional activity is my teaching. I really liked teaching courses and classes to students. I have estimated that I have taught hydrology to about 1,000 or 2,000 students, either engineering students or master students. And I have supervised or co-supervised, sometimes with Benoît Noetinger, about 100 PhD theses. And really, this is what I liked, and I hope all the students who worked with me on their PhDs enjoyed that as much as I did working with them. Now, for the question about the social role of scientists in technical problems in society, and I think my major contribution in the French case was that, as I said earlier, France was initially interested in granite. And personally, I thought granite is probably the worst type of rocks in which to store nuclear waste, because they are fractured, and through these fractures water can flow and can make the solute dissolved from the waste to become pollutant of the environment. So my major role, I believe, was in France with a colleague or two to transform the French program from looking to granite and change that to looking to clay, as the Italian had done, because clay is probably, in my view, the best medium in which one can safely store nuclear waste in the ground. So this is, I believe, my major contribution to scientific knowledge to society. I have also worked at the request of the French Minister of Environment on a waste disposal site for chemical waste, not nuclear waste. And this was in central France, in Montchanin. And the problem was socially, I would say, resolved, because the people had accepted that the solution which we had worked on could be accepted. So I think scientists have a responsibility to make technical solutions or scientific findings for practical problems understandable to the public and explain to them that they can safely go and do what is recommended.
According to you, what are the main states of modern hydrology from data acquisition to the underlying theoretical foundations?
Well, the major problem of hydrology, in my view, is that the population of the world, which is about 7.5 billion today, is going to reach 9 or 9.5 in 2050, and maybe 12.5 in the 1200th century. How are we going to feed and protect and permit the people to live with that many people? So the major problem that I see as a hydrologist is availability of water in the world at any scale, at any location, given the demand for feeding and giving water to that many people. And I think as a hydrologist, the main question is storage of water. We have to store water. We cannot live with the current system, which is to collect the water that falls from the sky, and they say that will be enough. I'll give you a simple example. In Burkina Faso, in Africa, it rains as much as in Paris. However, in Paris we have a more or less even distribution of rainfall every month. Well, it fluctuates from month to month, but it's not very different from one month to the other. In Burkina Faso, all the same amount of rain that falls in Paris comes into 3 months, and the 9 following months there's no rain at all. How can you live in that country if you don't have storage? So well, you can build dams, but dams have environmental consequences which are not easy to resolve. So my claim is that we can store water in the aquifers, in groundwater. So the main technical question of groundwater today, to me, is storage of water in aquifers. The next scientific question is chemical transport in aquifers, is to say how much pollutants can interact with the solids of the rocks, and so it's transport of fluids interacting with the medium, and this is a technical question, mathematical question, which really needs to be better looked at, and there's research needs to do that.